Okay, so Joseph Gay-Lussac is the one that looked at the relationship between pressure and temperature. Make sure that your temperature is in Kelvin here. He discovered that if the Kelvin temperature increases, the pressure will also increase. So that means this is a direct relationship. And just to help you out, maybe you already know this, but when you've got two variables next to each other, like pressure and volume are next to each other here, they are inversely related, okay? But when you have two variables on opposing sides of this division symbol, they are directly related. So like volume and temperature in Kelvin are directly related. Pressure and temperature in Kelvin are directly related because they're on opposing sides of that division symbol, okay? Okay, let's take a look at the next page. There's more donuts on my desk if you want more. Okay, let's look here. Here I've got a pressure of 1 atmosphere. So this is going to be my P1. Let's say my P2 is 2 atmospheres. You can tell that the pressure is increasing because the particles that are in the container are moving more rapidly and more vigorously, okay? So the more that those particles collide with the surface of their container, the higher the pressure will be. Here I've got ice and here I've got boiling water. Well, if the pressure increased by 2, doesn't that mean that your temperature also has to do the same thing because they're directly related? So let's say T1 is something like, and I'm just making up numbers here, 1 Kelvin. That means my T2 would have to be 2 Kelvin. Agreed, because it would have to double. Okay, all right. Now, the two variables that are being held constant here are going to be N and V. So moles of gas and volume. Let's take a look at the graph. You know that if you plot two variables and they're directly related, there should be a linear relationship. You'll see a straight line. It goes to the origin. So that's what happens down here in this graph. So here is my pressure versus temperature in Kelvin going through the origin. Okay. If you are collecting data from a lab, you've got pressure and temperature data in Kelvin. If you take the pressure value and divide it by the temperature in Kelvin, you will get some constant number all the way down that set of data. That will be equal to K. And then the equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. Again, I strongly recommend cross-multiplying before you put any numbers into that equation, so that way you don't make any mistakes. Okay, so let's come down here. Cross-multiply that. Do something like that. Okay. All right, do I need to do a practice problem or you guys get it? You got this. Okay. All right, if I bring all three of these laws together, you get something called the combined gas law. So let's come over here to the combined gas law. So Boyle's, Charles, and Gay-Lussac's laws together are the combined gas law. It looks like this. I would recommend cross-multiplying before you put any numbers into the equation. If you have a problem that says that you are at STP, STP is standard temperature and pressure. It is assumed that you know what those values are. So that means your temperature has to be 0 degrees Celsius or 273 Kelvin. And then your pressure would have to be any of those pressures back in section 1.1 that were at sea level, like all the standard atmospheric pressures. 1 atmosphere, what was it, 760 millimeters of mercury, any of those work. Does that make sense? Okay. They may not tell you what those values are. They'll just say you're at STP, and then it's assumed that you know. Okay. So let's take a look at a practice problem. Do I need to do one with STP just so you can see? Yeah? Number 2. Let's do this one. While in the hospital, Dr. Bundelow decided to remove a wart from Zippy's big toe. The doctor used a gaseous anesthetic to prepare Zippy for the operation. The gas, which was a nitrogen compound, occupies a volume of 18 liters at a pressure of 44 kilopascals, a temperature of 125 degrees C. We want to know what the volume is going to be at STP. So this is V1, P1, T1. If you add 273 to that, what do you get? 295, no. 273 plus 125, 398. And then we want to solve for V2. So your P2 and your T2. T2 would have to be 273 Kelvin because it's 0 degrees Celsius. Look at your pressure unit for P1 to help you get the pressure unit for P2. Okay, since it's in kilopascals, look back at section 1.1. What does it say at sea level kilopascals is? So that's what you would use here. I'm going to leave the units out just for simplicity purposes. Okay, so what you're going to do is divide both sides by 101.3 and 398, so these cancel, leaving you with V2. And then you should end up with 5.41 liters. Okay. At this point, we're done with all of the gas laws that involve some sort of a change. Okay. So all of the gas laws that we just did had like duplicates for volume or temperature or pressure. We're going to move into a gas law that only has one of each, okay? So that's how you know when to use one of these gas laws where there's some sort of a change versus when there's not a change, okay? So when there's not a change, you're using the ideal gas law, which is next, okay? So the ideal gas law is the one where it matters what units you're using. Okay, so here, the ideal gas law, which would be given to you, is PV equals nRT. Some teachers will pronounce it as PivNert. P is pressure of the gas. The unit for pressure depends on the pressure unit in R, which I'll talk about in a second. R is the ideal gas constant, and there are actually a few different numbers that you could use. It just depends upon what you're given in the problem, okay? V stands for volume. Volume absolutely has to be in liters. It cannot be in any other unit. N would be the quantity of gas in moles. R is your ideal gas constant. T would be your temperature, and that absolutely has to be in Kelvin. There's no such thing as degrees. That's a typo in the book. Okay? Okay, now let's move on to how we came up with this ideal constant value. So let's turn to the next page. The ideal constant value was derived. You don't have to worry about doing the derivation. I'm just explaining it to you. Basically, Avogadro's hypothesis said that if I have a mole of any gas, it will occupy the same volume as long as the temperature and pressure are constant. So here they're showing you have a mole of helium, nitrogen, and carbon monoxide gas. The pressure and the temperature are constant. They're all 1 atmosphere and 0 degrees Celsius. The volume occupied by each one of these gases is the same. It's 22.4 liters. If you put these values into the ideal gas equation, you can solve for R, and that's how they got the R values. So if we come down here, I can't remember if they put them all here. Okay, let's use them over here. They're showing you how they did it here in the quick check. We're not going to do that, okay? So here are the R values. You will sometimes see these shortened. For instance, I think in your book, does it say 8.31 or 8.314?
8.314.
Yeah. 8.314?
Yes.
I would probably use 8.31. And this one I would probably use 0.0821. And this one I would use 62.4. And then I think we're missing one. So let me highlight the pressure unit in these. If your pressure unit is in kilopascals, you're going to use 8.31. If it's in atmospheres, you're going to use this 0.0821. If pressure is in torr, you're going to use 62.4. Okay. There is one more value which is not in this. It's 1.21, which you don't see that much, but 1.21 liters times PSI divided by mole times Kelvin. If your pressure is in PSI, then you would use the 1.21. You do not memorize these values. I would give these to you to use. Okay. A couple of other equivalencies that are in the paragraph just underneath this, you might use later down the line. So let me scoot this over. If you've got a force of 1 Newton, that's the same as a kilopascal times a liter. And then you probably won't use that unless you go to physics. Okay. God bless you. All right. Let's talk about what an ideal gas is. There are 2 assumptions that we make about gases in order to use the ideal gas equation. So those 2 assumptions are molecules of a gas have virtually no volume. That's because the molecules of a gas are infinitely small in comparison to all of the space in between them. So this is your first assumption. The second assumption is that there are no attractive forces between your gas particles. So what that means is as they collide, they don't lose any energy as they collide, and then they keep on moving as if they never had. In reality, gases do have some volume and a little bit of attractive forces, but we're ignoring that when we use the ideal gas equation. Now, ideal gas conditions, you should know. Ideal gas conditions would be high temperatures and low pressure. You go to a low temperature and a high pressure, gases will not behave ideally. Okay. Let's take a look at the next page. And we're almost done here.